Okay, in the last class we described Dijkstra's algorithm. It solves the problem for single source shortest path. And we had also modified the algorithm to recover the path. And I told you that Dijkstra, although it is a greedy algorithm, it's still globally optimal. And today we will see why. What we want to find out is, why does Dijkstra work? Why does greedy pay off? Okay, this is the question that we want to ask. Locally best solution is also a globally best solution. Now let's say, suppose, let's say we have the set of source vertices here, and let's say this is the source, and there is a vertex W here, and there's another vertex X over here. So we are interested in the distance of W from S, which is outside S. Okay. Let us assume that W has a special path from S, which is shorter. So we assume that there is a special path from the source S to W, which is shorter. Okay. And shorter, and W is outside S. The source vertex listed. So that means what if it's shorter and it could have gone through some other vertex X. Okay. So clearly, what is this kind of thing? That means what we are saying is this path is has a special path from S, which is shorter, and W is outside. So that means you're going through some X and coming in and out of S and going to W. Other than the path that we are looking at. If this path is shorter, that means which is the path that we're talking about? We're talking about this path. This one. If this path is shorter, this implies S to X is shorter, and shorter than, remember the all distances are positive, right? Shorter than S to W because it's going by X, then X should have been selected instead of W. Okay. Clearly, as I already mentioned, the argument that distances are non-negative is important. Another possibility is we have S here, W which is outside, and this X which is inside will be what we are saying is there is a path from S to W to X and V which is shorter than S to X to V. Clearly again, clearly X is already in S and was seen earlier. Okay. Again, since distances are positive, non-negative, it is not, we can argue that it is not possible. Okay. So we looked at two cases. In one case where the X was outside, another case where X is inside. Go to a W outside. So what you're saying is, you go to in this earlier example for here, what we're doing, going to a X outside, coming into S and going to W, one situation. And the other situation is, you're going out to a W which is outside S, coming into X and going to V. And if these are short special paths, is it possible? And we argue that it's not possible because by the algorithm, by the definition of the algorithm, D of W, W should have been included before. W should be included before X. Okay, in either case. What's the time complexity of the single source shortest path problem? Complexity is order of n squared, where n is the number of vertices. If E is much less than n squared, we can use an adjacency list representation, and of the digraph, and can also use a priority queue, partially ordered tree to organize B minus S, and the time complexity can reduce to order of E log n. Basically, the idea is to go down the adjacency list for W and update distances in a priority queue. Total number of updates is E. Each update costs log n. Therefore, we have E log n. Okay. So it's possible to get an order E log n algorithm for solving Dijkstra.